potentials are graded. They can be either depolarizations or hyperpolarizations, and as we will see, they are created by things such as simple as mechanical deformation, as mechanoreceptors, or complicated biochemistry, which we'll talk about later as an photoreceptor. Now, what is not shown here is that receptor potentials are decrementally conducted away from their site of origin. You know what decremental conduction is, right? The reduction in size of the response as opposed to an action potential, which is always the same amplitude. Under certain conditions, is always the same amplitude. Right? So this is a decrementally conducted response. Now there is a specific form of a receptor potential called a generator potential. The generator potential is simply the receptor potential in a primary sensory act. And it gets its name historically when people were looking at these primary afferents. They saw that if you delivered a stimulus to them, you got depolarization. The more intense the stimulus, the larger the depolarization energy intensity was large enough, these things would generate an action potential, hence the name generator potential. But they're simply a form of, they are the receptor potential of the primary sensory ending. Now, another aspect of receptors is that of adaptation. Adaptation is the decrease in response of a receptor to a sustained stimulus. Now, we can, in general, classify two types of receptors based on their response to a maintained stimulus. One type is shown here on the left. Here is our stimulus box up here. These are tonic or slowly adapting receptors. You can see that not only does the receptor potential, not only is the receptor potential maintained throughout the duration of the stimulus, but so is the action potentials produced by that receptor potential. Now there's another very different type of receptor, which is called a phasic receptor, or a rapidly adapting receptor. And here you can see that both the receptor potential and the action potential activity are confined to the onset and off of the stimulus. Nothing in between. So for these, the brain gets no information except for the onset and offset of the stimulus. Now, there is a characteristic of the rapidly adapting phasic receptor, which is not obvious on that slide, which is obvious here. Here's the stimulus that I showed you in the previous slide. Square pulse produces a response only at the beginning and the end of the pulse. However, down here, if you give a stimulus which is changing, what you see is that the rapidly adapting receptors follow the change in stimulus. And if you were to give this stimulus at a different rate, you would see that the frequency of action potentials would mimic the rate of change in the stimulus. So rapidly adapting receptors are very good at relaying information about the rate of change of a stimulus. As soon as the stimulus becomes constant, however, they stop relaying any information. Now, adaptation occurs for two primary reasons, and one of them can be demonstrated here using a receptor we'll talk about in a moment. It's called a singing corpuscle. This is a receptor that's called an encapsulated receptor because the primary afferent terminal is enveloped in this laminae of an onion skin-like connective tissue. There's actually fluid filled. Now this is a stimulus here, and what that stimulus is you take a probe and you push on the onion skin. That's a stimulus, and you maintain that portion. And what you see, if you're recording from the ending itself, is that the receptor potential is exactly like a rapidly adapting receptor field potential. It's there at the on, and there at the off, and nothing in between. This can be explained by structural adaptation. What is going on here is that as you first apply the probe, there is a pressure gradient that is immediately established. That pressure gradient stimulates the sensory ending. However, very quickly, the fluid within the capsule rearranges itself to dissipate the pressure gradient. So the pressure gradient goes away very quickly. And when it goes away, so does the receptor potential. When you withdraw the probe, the pressure gradient returns, but in the opposite direction, so does the receptor. That this is actually the case can be demonstrated by stripping the onion layers of the encapsulation off and looking at the bare sensory ending. And now when you apply the same stimulus, you get a very different response. The receptor potential now is maintained throughout the duration, more or less, the duration of the stimulus, as is the potential frequency. So this is an example of structural adaptation. Rapidly adapting receptor is because of the encapsulation of its ending. Now there's another reason for adaptation, which is accommodation. Accommodation is essentially produced by inactivation of voltage-gated channels because of a maintained depolarization. So the most likely channels, sodium, voltage-gated sodium channels, but also voltage-gated calcium channels, in some cases also happen. You maintain a depolarization, they inactivate, the channel become non-functional. Now another property of a sensory receptor is its receptive field. And this can be easily demonstrated for a cutaneous receptor. So here you have three primary afferent neurons, and you say, all right, what is the receptive field here of this blue neuron? And the way you find out is you go out to the periphery someplace and you start poking the skin until you can activate this neuron. And as soon as you can, then you mark the area where poking the skin activates this neuron, and you have its receptive field. If you do this for these other two, you can map the receptive field of those neurons. Now, if you increase the complexity of the question and go into the central nervous system and say, what is the receptive field of this second order neuron? The answer is quite simple. It's just the sum of all of its inputs. So if you say, what is this receptive field? You just go out and it's out here given by this bluish, purplish line, whatever it is, which is the sum of the individual inputs. This is the same thing, exactly the same is going to apply when we get into vision and talk about receptive fields of ganglion cells. But for some reason, when I get there, you'll forget this. Because the stimulus will be a spot of light on the retina, not a prod to the skin on someplace on the body. Now, certain attributes of the stimulus can be made more understandable to the nervous system by the way they're presented, and that is called coding. And the first coding that we're going to talk about is that of modality. Modality says, what is this? What does the stimulus mean? Is it vision? Is it smell? Is it hearing? What is this sensation? And that is accomplished by the wiring of the central nervous system, which is called labeled line. First of all, receptors respond specifically, most sensitive to a specific type of stimulus. That information is carried by an axon to the central nervous system, where it goes to very specific places. For instance, visual information is relayed to the visual cortex. Stimulation of the visual cortex produces the sensation of vision. It doesn't matter how it is stimulated, whether it's actually light coming into the eye, or it is you getting banged on the head. You see stars banged on the head. Because the primary visual cortex is stimulated, any stimulation of that region of the brain will be interpreted as vision. The same applies for the auditory cortex, for instance, as with baroreceptor. Stimulation here produces sound. Doesn't matter how it happens. Primary somatosensory cortex, same thing. Stimulation there produces perception of mechanosensation. Now the location of the stimulus is how is that encoded? That again is most readily shown by using cutaneous receptors. It is again in the specific wiring of the nervous system. Input from the hand, for instance, goes to this region of the brain. Stimulation of this region of the brain evokes the sensation of touch to the hand. Now, it doesn't matter how it occurs. If we have time, when I speak about some remodeling of the brain that occurs in phantom limb pain, you'll see that often this sensation is inappropriate. The brain is interpreting the hand as being stimulated when the hand has been amputated. It's because of information coming into this area of the brain. Now, the intensity of the stimulus occurs for several reasons. If we look at the responsive receptor, what we see is that if you give a weak stimulus, if the generator potential, or this generator potential, except it is a primary sensory acronym, this would probably be better if the same receptor potential. The receptor potential is sub-threshold. There are no action potentials produced. The brain is completely unaware of anything happening. Increase the intensity, not only now exceed threshold and produce action potentials, but they come at a certain frequency. If you increase the intensity, the frequency of the action potentials increases. So frequency of action potentials is one way in which intensity can be relayed. The other is by the following. If I take this pin and I just lay it on the top of my hand, the pin depresses very slightly the skin of my hand and stimulates those mechanoreceptors just beneath the tip of the pin. That information is relayed as touch, and I feel it. Now, if I press down a little bit, two things happen. One, I more forcefully stimulate the receptors right underneath the pin, so they become excited and the frequency goes up even more. But secondarily, I'm indenting the skin, and I am stimulating now receptors surrounding the area where the actual pinpoint is. So I've increased the number of receptors now responding. Same sort, but I've increased their number. That's another way the brain can measure increase in intensity. So we have the increase in frequency just underlying the pinpoint, and the increase in the number of surrounding receptors. Now, if I press really hard, I begin to involve deep receptors. So now I'm stimulating a completely different population of receptors. The increase in not only the frequency of action potentials of the original receptors, the increase in population of the light receptors on the surface, but also now another population of receptors becoming active tells the brain the stimulus must have increased quite a bit. So there's several ways in which the brain can judge the intensity of stimulus.